In this talk, I want to first introduce you to Continental's vision on augmented reality head-up displays. And then I want to introduce a prototype with which we approach this vision. So today in a car, there is a lot of information available to the driver, and we think it's too much input to all pull that onto the driver. So we want to make driving a relaxing experience and do not want to put too much information to the driver. So our vision is that we provide the information the driver really needs in the most relevant and intuitive way. So with augmented reality, for example, if you pick up a friend from the airport, the car should inform you that your friend is waiting on the right side of the road and not push all available information onto you. In terms of automated driving, we want to use augmented reality as a way to provide confidence to the driver, so that, or passenger, so that you do not feel as a victim of the car doing anything and you don't understand why it is doing that, but the car should communicate to you and let you know how it perceives the current situation in which you're driving and why it is doing what it is doing. So we have prepared a short video for that. So on the right side of the road, there's a broken down vehicle. So the car tells you, I have recognized that there's a danger and slowing down for that specific reason. Today's head-up displays, at least the majority of it you currently have on the road, shows you a virtual image. We call that projection distance. It's 2 meters in front of the driver, which means it is at the front of the car, right above the hood, and it just provides you some information as symbols. So the typical field of view for such a head-up display is 6 times 2 degrees. And for augmented reality, you need a little more. What you want is to provide an image to level up slightly above the horizon and in a certain distance from your car. So this defines a height of 5 degrees, which would be useful for an augmented reality car. And in terms of width, you would like to cover not only your lane, but at least a bit of the neighboring lanes, so that you can use a proper augmentation. Also for augmented reality, it is not wished that you provide the image directly in front of the car. It's better for augmentation to have it at a higher distance. So we did experiments with 7.5 meters in the past. Our current demonstrator targets an infinite projection distance, which is quite a benefit. The technical specifications you need for such a head-up display are different than a standard head-up display. And we approach this in certain steps. So this is what the majority of cars currently have. We have also some examples on the roads with a slightly bigger image, something like 9 times 3 degree. And then we leave the world of conventional head-up displays and go into the world of augmented reality head-ups, and this starts with something like 10 times 5 degree as a single layer at a projection distance of 10 meters. Then we have a combination of what you have right now and the augmentation with a 2-layer display. So here we have 10 times 5 degree as the augmented layer, and as a classical information layer also at 2 meters that 6 times 2 degree, and the full augmented reality head-up display would be something like 15 times 5 degree at a large projection distance, so 50 meters infinity, something in that range. With conventional technology, which today means you have a mirror optics providing the virtual image to the driver, you would need for a field of view of 15 times 5 degree, a volume of 30 liters, which is basically not available in that position of a car. So it is not feasible to provide augmented reality with 15 times 5 degree as a serious solution in conventional technology. This is why we are investigating Waveguide technology as an enabler for augmented reality head-up displays, and provide a head-up display with about 10 liters with a stack of waveguides over here and a projector at its side. So what we are basically trying to do is to do the same what happened with television. You're going away from bulky 3D devices to flat devices enabling larger images. So to do that disruptive transformation from a classical head-up display to a waveguide head-up display with a larger field of view. The approach we are following is what most of you probably know from that head-mounted display. So we are doing this in cooperation with DigiLens, and they have experience with head-mounted displays doing exit pupil expansion to provide a virtual image to a driver in a wearable device. And I just repeat the principle of operation for that. So you have some spatial light modulator providing a pixel, and this pixel is collimated into a beam by an objective. So this is a projection unit. Then you have an input hologram which transform that incoming light into TIR mode traveling through the waveguide. And in that waveguide layer, you have also an output hologram which couples out the light again, but not completely, but portion by portion, so that the light is available at in larger areas. So you would see already the same point when you looked into the projector, but the waveguide principle allows you to see the image from different positions. So what your eye does is it focuses again that incoming light onto a single spot in the retina, and so you see a spot corresponding to that pixel when you look into that waveguide. And you see the same spot for different positions, so it doesn't play a role where your eye is. You always see the same image, and that's a principle of exit pupil expansion. And if we change the pixel over here, then it changes the angle under which the light is propagating and the light is exiting, and you see the pixel at a different position, and with several pixels you can create a full image. So we are doing 2D exit pupil expansion. So we are coupling light with a projector into an input grating, then have a first direction exit pupil expansion. So the light is traveling in the waveguide up here. In this area, we have a fold grating. The fold grating deflects the light, so that's propagating in that direction. And finally, we have an output area where the image is coupled out again of the waveguides, reflected by the windscreen, and is visible as a virtual image from the driver's eye. So this stack of waveguides here in a CAD model is here is a photo from our demonstrator from CES 2018. And there we presented a prototype of a first full-color holographic waveguide head-up display. So here you have the projector. Here you have a stack of waveguides, one for red color, green color, blue color. And here you have a flat piece of glass resembling the windscreen. And here's a demonstration with the virtual image. Here on the projector, it looks not so nice. It looked nicer in reality, but we have shown a virtual image with a field of view of 15 times 5 degrees and a projection distance of infinity. So after that, the next step was to integrate the windshield compensation into the waveguide. So you always have with windshield head-up display a curved windshield, which acts as an optical element but is not designed as one. And so you have to compensate the behavior in optical manners to have a proper image display, a stable image display over the field of view again. And so what we did is to integrate the windshield compensation in the output hologram. With a curved windshield, we had to also use the curved grating. And as a side effect, the dispersion effects in the holograms do not compensate completely anymore. So we would have dispersion effects with a broadband light source. And as a second step, we also had to switch to an laser-driven projector with more narrow-banded light sources. And this is called car demo because we integrated it into a car, which was the purpose of this. So we have here the waveguide stack, which is outputting the light towards the windscreen, and then the driver can see it. Here you see its position in CAD model. So we integrated it in the car. After that, we also closed the dashboard properly so that it really looks like you're used to a car today. And the specification of this is we have infinite projection distance, a field of view of 11.5 times 3.6 degree, and the eye box size, so the area, the virtual image is completely visible, of 140 times 70 millimeters. And we have demonstrations running. This is at our plant in Babenhausen, showing the use cases we are intending. And here you see the area of the dashboard where the waveguide is integrated. And here the augmentation. So the car is pulling your attention to that there's a broken down vehicle standing on the side of the road, and you have to pass that one. The video I'm showing you next is taken with a smartphone, so it has some color artifacts which are not visible in reality. It's a term of synchronization between the projector and the camera, but it gives you an impression how augmentation works in our demonstrator. So we're approaching a right turn here, and the arrows are showing you the direction where you really have to go in an intuitive way. So to sum it up, for augmented reality head-up displays, you need a larger field of view. So target would be about 15 times 5 degree. We've built a demonstrator which included compensation of the windshield curvature in virtual image generation and projection distance of infinity, first time for a windshield head-up display, and it's also important for our customers as an experience. How does such a projection distance looks like in a driving experience? Okay, any questions? By the way, thank you, and also the team for which was involved in making that prototype ready and drivable.
Yes. Will it be possible to put the waveguide inside the windshield, or you don't want that?
There were ideas doing something like that. We currently do not have a solution for getting a wave 2D exit pupil expander in a curved piece of glass for more than a few bounces. So with a large exit pupil expander, you need a lot of bounces, and we are currently not able to maintain a virtual image over a distance in such a system. And the other aspect, it is based on total internal reflection. So the light is guided through the glass. And if you would have something like raindrops, you would lose the guided light because the raindrops would couple it out. So you can play with things like a refractive index and really make a guided mode so that you have something like a core and a cladding, and then guide an image through it. But like we are currently doing it, so using the interface air glass for guiding the light. It would fail if the glass gets wet or dirty. So not a good idea in the windscreen if you want to do it with that air glass interface.
Here, let me give you the...
You switched from a broadband light source of the LED to the laser.
Correct.
Curved. Is that something that's just at this stage of development, or is it fundamental that with a curved windscreen you have to go to something like a laser?
It is pretty fundamental because with a classical waveguide, you can describe the gratings by k-vectors, which are more or less wave numbers. And you can use the situation that these gratings compensate fully. So the light is entering under exactly the same angle like it's exiting. And then you have a compensation of the dispersion effects. So in the waveguide, every wavelength travels as on a slightly different angle. But when you have passed all holograms and the sum of your k-vectors is 0, then that dispersion is compensated again. So you do not have a net dispersion effect in this case. But when you start to curve your output grating, you only have one position where this is true. But on all other positions, the further you go to the edge of the exit pupil, the stronger the dispersion gets. And so with the semiconductor lasers with a bandwidth of 2 or 2.5 nanometers, we are in the acceptable range. If you would use a LED with that curved windshield compensation, you would see the pixels at the edge of the vertical image being blurred into streaks going outside.
Any other questions?
Can you tell us something about the resolution of the device in pixels?
Resolution is full HD. So
Thank you.
Okay.
Okay, anyone else? Going, gone. Thank you so much.
There's
And-
one.
Oh, do we have this one?
Yes, light losses are an issue, and we are working on increasing the efficiency, and also still working on increasing image quality, but it's getting better and better every month, and we are reaching a reasonable level right now.